All right, now we're looking at our rock's displacement at 2 seconds. So S of 2, I can just read from my table, 35.4. S of 4 is 6.6. Looking at this, my 35.4 minus 6.6 over the 2, what we're looking at here is, we know that our rock is moving down. So we have our 6.6 minus the 35.4. So 6.6 minus 35.4, negative 28.8, divide that by 2, and we get negative 14.4. If I think about units here, this is meters per second. This is our average speed between 2 to 4 seconds. So this is the average speed. If we continue on looking at our notes, velocity talks about our change of distance with respect to time. So average velocity is what we just calculated, delta S over delta T. Instantaneous velocity is we want to know the velocity at exactly t equals 2 seconds. Well, that's going to be our limit as h approaches 0 for s of whatever the time value we're looking at plus h. So in this case, if I wanted at 2 seconds, it would be 2 plus h minus s of t, or in this case s of 2, divided by my difference in time. So of course that's going to be h. Looking at this of course is our first principles definition of the derivative. So instantaneous velocity is the first derivative of displacement. So if we continue on with our example, the average velocity from 2 to 3 seconds, so not going all the way this time to 4, but going from 2 to 3. So we're going to have 25.9 minus 35.4. So we could call this velocity from 3 to 2 seconds. 25.9 minus 35.4 over 1 second. So that's going to be negative a half. Oh no, not a half, of course, because we're going for more than that, negative 9.5 meters per second. So thinking about this, really what I've done is, if I come back to my graph, if we think about what we've done here, we have, goodness, what we're really doing is putting in a secant between 2 to 3 seconds. So what we're really asking ourselves is which slope is steeper, and if we're comparing our instantaneous velocity at 2 seconds, that means we're looking at the tangent. So approximating going from 2 to 3 seconds, we're going to assume we're going faster than we actually were at 2 seconds. At 2 seconds, we had just started our descent again. At 3 seconds, we've been falling for over a second. So now, if I find my velocity at t equals 2, well, that's going to be found by plugging 2 into my first derivative. So my first derivative is going to be negative 9.8 times 2 plus 15. So I've just taken the derivative. So of course we're going to have negative 9.8 t plus 15. Plugging in the 2 for my t is going to give me my instantaneous velocity. So I could also calculate that with my graph. So I'm going to calculate dy dx at x equals 2. And I get that my derivative value, or my instantaneous velocity, is negative 4.6 meters per second. So technically this one is larger because it's less negative. And really what that means is that my instantaneous velocity is slower than if I look at my average velocity between those 2 points.